If you're tracking, you should have obtained the following results. For our first example problem expressed in polar format as 6.6 at an angle of 33.2 degrees, the real component is 5.5. Conversion is necessary because we're being asked to find a rectangular element of a complex number being expressed in polar. The imaginary component is 3.6. Similarly, conversion is necessary because we're being asked to find a rectangular element of a complex number being expressed in polar. Magnitude is 6.6. No conversion is necessary since we're originally given polar format. All you got to do is be smart enough to figure out which one's the magnitude. The angle is 33.2 degrees. Similarly, no conversion is necessary since we're originally given polar format. All you got to do is be smart enough to figure out which one is the angle. By the way, it's the one with the degrees attached to it. For our second example problem, A expressed in rectangular format is 6.7 minus J 6.0. The real component is 6.7. No conversion is necessary since we're originally given rectangular format. All you got to do is be smart enough to figure out which one is the real component. By the way, it's the one without the J. The imaginary component is negative 6. No conversion is necessary since we're originally given rectangular format. All you got to do is be smart enough to figure out which is the imaginary component. It's the one with the J. The magnitude is 9.0. Conversion is necessary because we're being asked to find a polar element of a complex number being expressed in rectangular. Finally, the angle is negative 41.8 degrees. Similarly, conversion is necessary because we're being asked to find a polar element of a complex number being expressed in rectangular. Moving on, let's now examine negation and complex conjugation, two related but totally different functions that are often confused with each other. Let's first examine the negation of complex numbers using rectangular format first. Negation can be performed by multiplying a complex number expressed in rectangular format by -1, with the understanding that one must multiply the complete complex number by -1. This is most easily accomplished by enclosing the complex number using rectangular format in parentheses. Given complex number A using rectangular format is 3.9 plus J 5.9, the negation negative A is negative 3.9 minus J 5.9. When we illustrate both these complex numbers on a graph, A and negative A point in two totally opposite directions, as we'd expect. Let's now examine the negation of complex numbers using polar format. There are two methods of negating complex numbers using polar format. One can multiply the magnitude by -1, keep the angle the same, or two, one can keep the magnitude the same and add or subtract 180 from the angle. Given complex number A using polar format is 3.7 at an angle of 143.7 degrees, the negation negative A is either negative 3.7 at an angle of 143.7 degrees using the first method, or 3.7 at an angle of negative 36.3 degrees using the second method. While these are equivalent, the format 3.7 at an angle of negative 36.3 degrees is preferred, since it makes it exceedingly obvious the magnitude is the same, only it's pointed in the opposite direction. Let's now examine the complex conjugate. For some reason, students historically struggle with this concept, despite it being the simplest of tasks. If negation of complex numbers is to be likened to complete, totally opposite reversal, complex conjugation is to be likened to reflection. Don't make the complex conjugate hard. If given a complex number in rectangular format is x plus jy, the complex conjugate is x minus jy. If given a complex number in polar format is z at an angle theta, the complex conjugate is z at an angle of negative theta. Can you dig it? The complex conjugate is simply the reflection of the original complex number across the x-axis. For example, consider complex number A in rectangular format as 3.9 plus J 5.9. The complex conjugate of A, often symbolized as A star, is 3.9 minus J 5.9. The complex conjugate is a reflection of the original complex number across the x-axis. Let's try another example. Consider complex number A in polar format as 3.7 at an angle of 143.7 degrees. The complex conjugate A star is 3.7 at an angle of negative 143.7 degrees. Again, the complex conjugate is a reflection of the original complex number across the x-axis. don't make the complex conjugate hard. Let's put your understanding of negation and the complex conjugate to the test with this set of example problems. Given a complex number in a particular format, determine the negation and complex conjugate in the original format. By all means, pause the lecture and try this on your own. If you're tracking, you should have obtained the following results. For our first example problem, complex number A in rectangular format is 2.2 plus j 1.8. Negative A in rectangular format is negative 2.2 minus j 1.8. Negative A appears to be pointed in the opposite direction as A, as we can expect. The complex conjugate of A in rectangular format is 2.2 minus j 1.8. The complex conjugate of A appears to be the reflection of A across the horizontal axis, as can be expected. For our second example problem, negative B in polar format is 10.9 at an angle of 150.8 degrees. As can be expected, negative B is pointed in the opposite direction as B. The complex conjugate of B expressed in polar format is 10.9 at an angle of positive 29.2 degrees. As can be expected, the complex conjugate of B appears to be the reflection of B across the horizontal axis. Moving on, let's wrap up our discussion of complex number math with a couple challenge problems. Given you're familiar with both rectangular and polar format, can perform conversions between rectangular and polar format and vice versa, are capable of adding, subtracting, multiplying, dividing, and now negating and forming the complex conjugate of complex numbers, as well as disassociating a complex number into its individual real, imaginary, magnitude, and angle components, you should be capable of rising to these challenges. But by no means are they a mindless task of merely using a formula as previously, but rather these tests necessitate synthesis of all the above concepts to arrive at an answer. Challenge 1. Given a complex number known to be in the first quadrant with a magnitude of 6.2 and a real horizontal x component of 1.4, determine the imaginary y component and the angle. In this scenario, we've been given only partial information about the polar and partial information about the rectangular means of representing the same complex number. In the case of the rectangular representation, we've been given only the real component, but not the imaginary. In the case of the polar representation, we've been given the magnitude, but not the angle. Do you have what it takes to solve for the imaginary component and the angle? If you've got the level of understanding of complex numbers, conversion, and algebraic manipulation I expect you to possess, you should. If you feel you're up to the challenge, by all means, pause the lecture and try this on your own. If you're tracking, you should have obtained the following results. Key to the solution of this problem is your understanding of conversion between rectangular and polar formats. Recall we've established 4 key formulas for the purpose of conversion. The real horizontal x component is the magnitude times the cosine of the angle theta. The imaginary vertical y component is the magnitude z times the sine of the angle theta. The magnitude z is the square root of the sum of the squares of the real and imaginary components. And finally, the angle theta is the inverse tangent of the imaginary over the real component, with the understanding that angles in the first quadrant are from 0 to positive 90, angles in the second quadrant are from positive 90 to positive 180, angles in the fourth quadrant are from 0 to negative 90, and angles in the third quadrant are from negative 90 to negative 180. If you did not arrive at a solution previously, you should be able to now, given it's right in front of you. If you're still missing it, I direct your attention to this formula here. The real horizontal x component is the magnitude z times the cosine of the angle theta. Given we know the magnitude z and the real component x of our given complex number, the logical handhold to begin our climb is the only conversion involving the magnitude and real component of our given number. Let's use our 2 knowns, the magnitude z and the real component x, to solve for our single unknown, the angle. Rearranging the conversion and taking the inverse cosine of both sides, we arrive at the angle equals the inverse cosine of the real component over the magnitude. Substituting our given values yields an angle of 76.9 degrees. Now what? We've got 3 knowns, the magnitude, the real component, and the angle, and 1 unknown, the imaginary component. If you can't figure out what to do, I direct your attention to this formula here. The imaginary vertical y component is the magnitude z times the sine of the angle theta. Substituting our known values of magnitude and angle yields an imaginary component of 6. Ta-da! Our given complex number can be expressed using rectangular format as 1.4 plus j 6.0, or using polar format as 6.2 at an angle of 76.9 degrees. Okay, it's your turn. This time you're on your own. By all means, pause the lecture and try these by yourself. For our first example problem, we're given a complex number known to be in the fourth quadrant with a magnitude of 11.6 and a real component of 7.8. Solve for the angle and the vertical imaginary y component. Given we're in the fourth quadrant, it should be readily apparent that our resultant angle will be between 0 and negative 90 degrees, and our resultant vertical imaginary y component will be negative. For our second example problem, we're given a complex number known to be in the first quadrant with a real component of 2.3 and a magnitude of 5.4. Given we're in the first quadrant, it should be readily apparent that our resultant angle will be between 0 and positive 90 degrees, and our vertical imaginary y component will be positive. If you're tracking, you should have obtained the following results. For our first example problem, the given complex number can be expressed using rectangular format as 7.8 minus j 8.6, or using polar format as 11.6 at an angle of negative 47.7 degrees, as these operations illustrate. Note, since we know that we are in the fourth quadrant, it necessitates active intervention on our part to ensure our angles between 0 and negative 90 degrees as we'd anticipate. For our second example problem, the given complex number can be expressed using rectangular format as 2.3 plus j 4.9, or using polar format as 5.4 at an angle of 64.8 degrees. Hopefully you did well in this last set of example problems, as these represent the synthesis of a number of the concepts we've thus far discussed. If you did well on these, you are on track. If you didn't do well, you are off track and need to get yourself back on track as soon as possible. By all means, rewind, revisit, or review any section you might be having difficulties with. We'll examine scientific calculators and complex numbers in later lectures that make some of these manual methods seem ponderous in comparison. However, your understanding of these basic concepts is still essential to manipulation and interpretation of complex numbers, especially when presented scenarios in which only partial information is available. In conclusion, this lecture presented math operations with complex numbers necessitating intermediate format conversion, isolation of individual complex number components, negation and complex conjugation of complex numbers, and determining individual complex number components given partial information. Remember to review this material as often as you need to really drive it home. Imagine how well lab will go if you know what you're doing. Thank you very much for your attention and interest, and we'll see you again during the next lecture of our series. Remember to tell your Lazy Lab partner about this resource, and be sure to check out the Big Bad Tech channel for additional resources and updates.